Welcome to the St. Petersburg Science Festival 2021 School Day. We're so glad you've chosen to join us for this session. We are going to have Gulf of Mexico Coastal Ocean Observing System, Dr. Chris Simonello, Grant Craig, and Abby Wakely. They're going to talk to us about decoding maritime signals and talk to us about the technology that we use to understand oceanic and atmospheric conditions that affect people and the economy. Thank you for joining us.
Thanks, Kara, and good afternoon, everybody. Thanks for joining us for our session, Decoding Maritime Signals. My name is Chris. I'm an oceanographer with Texas A&M University and the Outreach and Education Manager for the Gulf of Mexico Coastal Ocean Observing System. And presenting with me today are my colleagues, Grant Craig. I'm going to introduce here.
Hi, everyone. I'm Grant Craig. I'm with the Gulf of Mexico Coastal Ocean Observing System.
Hi, everyone. I'm Abby Wakely, and I work on communications for the Southeast Coastal Ocean Observing Regional Association, also known as SOCORA.
And we know that's a mouthful, but I'm going to switch over right now and share my screen with you. And thanks for your patience. And here we go. Okay. So we all work for a program called the U.S. Integrated Ocean Observing System. Grant and I work for GCOOS, which is the Gulf of Mexico. It includes Texas, Louisiana, Mississippi, Alabama, and Florida. And Abby is with SOCORA for the Southeast, which is North Carolina, South Carolina, Georgia, and Florida. And obviously we overlap in the area of Florida. And so we work together and collaborate on a lot of joint projects, this one included. So today we're going to learn 3 different things that we're going to focus on. How the U.S. Integrated Ocean Observing System benefits society. And that's in 3 main ways that we're going to talk about. We're going to talk about it from the point of view of public health, from the point of view of ecosystems, and looking at the economy. Then Grant is going to talk to us, and you're going to learn about the International Code of Signals. And then Abby is going to do some fun stuff, looking at how to make a classroom banner using the signals that are in the flags. So for the teachers and some of the students, as you're listening, if you don't already have your supplies together, here's a quick list of things that you'll need to join us later in the program. So it's just basically crayons and some cardstock. You can worry about the hole puncher and the string and putting together your banner at a later time. So here's Abby. She's going to talk to us about SOCORA first.
Hi, everyone. It's Abby again, and I work with SOCORA. And so SOCORA, as Chris mentioned, we're one of 11 trying to work to observe the ocean. And pictured here is what is called a coastal ocean observing system. It's a system from hardwares to humans working together to collect data on the ocean to answer questions like, what's the water temperature? Is there a hurricane coming? What's the wind speed of the hurricane? And pictured here, you'll see one of the technologies used to collect this data. It's called a buoy, and we have a mini version here, but you can see from the photo, they are quite large. And what they do is they sit on top of the water, and we put sensors on the buoys to collect data. And so here's one sensor, and as I spin it, maybe you guys can guess what this collects. It's called an anemometer, and it collects wind speed data. So it sits on top of the buoy, and it will tell us how fast the winds are blowing. And this data is really important for forecasting what's going to happen. So if you've ever been on a boat, you want to go out on a boat when it's smooth seas. If it's too choppy, there's too many waves, it's not safe. So this data here is used to help influence these forecasts to let us know if it's safe. Or if a hurricane's coming by, the buoy's in the water and the hurricane goes over it, it will tell us the wind speed, which helps say if we need to evacuate or stay put. And then Chris is going to tell us about another technology in a coastal ocean observing system.
Thanks, Abby. That was great. Abby talked to you about a buoy, which is a fixed platform. It's got a long mooring chain that sits on the bottom, and so the buoy sits in one place and collects a lot of information about that location. Another type of platform is called a glider. And the glider is a mobile platform. This one is a type of autonomous underwater vehicle, and it covers a much larger spatial area of the ocean. And they don't typically stay out as long as a buoy, 30 days, 90 days, several months in some cases. But like the buoy, you can put different types of sensors on the instrument, on the platform, that then tell you information about the mission that you're interested in. So maybe you're tracking hurricanes, maybe you're looking at hurricane intensity forecasts, maybe you're trying to track fish and sharks, and so you put hydrophones on there and look at the acoustic signal. Maybe you're tracking an oil spill or other contaminant, disaster spill, and you might be having optical sensors on there. So it really depends on the type of questions that you're asking, what kinds of sensors you would put on the platform. The Gandalf website is a tool that GCU's developed. If you're a fan of Lord of the Rings, you recognize the name. Our developer, Bob Currier, has a big fascination with Lord of the Rings, so he's always putting his little touches on things. But this is really a tool that was made to help the glider pilots fly their missions. And not only can they track the gliders, we also track those blue dots that you see there. Those are called drogues or drifters. They float around the ocean, just as the name implies. And they have temperatures, salinity, they can have sea surface height. There's different sensors that go on them. And then the modelers who make the forecast put that information into their models, and it gives information about ocean currents and the velocity and the speed and the direction that those currents are moving. And as Grant talks about some of the shipping industry needs, you'll see why this is very important. This is an example of a profile that was made from temperature data. This shows you at the surface, the water is very warm. It's almost 30 degrees at the surface. It goes all the way down to 800 meters, and the temperature gets very cool down there, about 5 degrees. But being able to see these conditions in near real time as the glider transmits information back is really important, especially if you're tracking living marine resources. You could see the lot of living things like to aggregate at the places where conditions change rapidly. We call them clines, a thermocline for temperature, a pycnocline for density. So there's different ways to look at that. This is another really cool tool called HabScope. It was recently developed by GCUS in partnership with NOAA and other partners. Traditionally, when scientists go out and monitor red tide, it takes a lot of people, human resources, and money to process samples. It can take several days by the time you take a sample to the time you get the results back. And so often that parcel of water that you sampled is not even there. So HabScope is run by a group of highly trained volunteers. They have the microscope with it was an iPod. It's moving now into something called Raspberry Pi. The volunteers collect a water sample. They put it on the slide. And the software that was developed using AI technology used over 60,000 images to train the software to recognize the Karenia brevis cell that's responsible for Florida's red tide when it sees it. And this is an example of the product that you see. It's those red tide cell counts that are made roughly every 3 hours. The forecast comes out compared to days with some of the other traditional methods. And it uses the National Weather Service information about currents and winds and the direction that they're blowing, because Karenia brevis produces a toxin, a neurotoxin. And when it gets into the breaking waves, it can break up, become aerosolized. The little water droplets that become sea spray can have the toxin in them. And so for most people, it just means you might cough or have to sneeze, have teary eyes. But for people who have respiratory conditions like asthma or COPD, it can be really dangerous. And so having this forecast is really a service for public health. I'm going to transition now. We're going to hand off to Grant, who's going to talk about the importance of communication on the high seas.
Hey, hello again, everyone. And just to remind you, too, that you can go to the GCUS website, the Socorro website, and see all of this information that's being collected by the remote sensing capabilities that Abby and Chris just talked about. What I'm going to talk about is the International Code of Signals. While these large commercial ships will use our data for safe navigation, they also need communication is very important as well for safe navigation on the high seas. And one of the things that allows for that is the International Code of Signals. It's an international system of signals and codes used by ships and vessels to communicate important messages on the high seas, especially in situations where language barriers could create a communication problem between vessels. Right. The system is made up of flags that you see on this slide from A to Z and using the numerals 1 to 10. You can see all of the letter flags most of them are squares with the exception of A and B, Alpha and Bravo, which have a little notch out of the front of them. And then the numerals are represented by triangular flags. All of the flags use one or more of 5 colors: blue, white, red, yellow, and black. very distinguishing colors that contrast each other when used on the flag so that there's no mistaking the messages trying to be communicated. This code of signals was developed in the 1850s. There were some codes and signals used prior to that, but the first version of this was in the mid-1800s as a need for communication became apparent on the high seas. More traffic, people from different countries speaking different language that needed to communicate with each other. And there's been lots of revisions based on events that have happened over the years. And the current code of signals being used was revised, is from the revision in 1965. And this really took the existing code of signals and focused it on safety of people and cargo as the most important thing. It got rid of a lot of the other types of communications that were part of it and really focused on safety of navigation and persons. Now, each letter that we talked about on the previous slide, if you look at the bottom example here, you have the letter C that's represented by the flag, the red, white, and blue flag next to it. Charlie is the name, so if they're trying to communicate over a radio, they don't say C. They'll say Charlie or Delta, Alpha. There's a name for each letter of the alphabet, and that comes from the phonetic alphabet, also used by the US military. And then on the bottom right of the slide there, you can see little slashes and dots. These can also be communicated by Morse code. So on lots of different situations that could arise, there's many different avenues that ships could communicate. If there was foggy weather and the radio signals were down, they could use air horns to communicate these messages through Morse code. And each letter of the alphabet has a message associated with it, which I'll get to on the next slide here. So if you look at this picture of this slide, we have lots of large vessels all in one spot. This can happen, especially in areas close to port. There's actually a situation much like this picture right here going on the West Coast outside of the ports of Los Angeles and the ports of Long Beach. There's a backup of dozens and dozens of vessels trying to get into that port to offload cargo. Those vessels are coming from all over the world in a tight spot, and they're going to need to communicate with each other. Let's have an example. If one of these ships in this picture was experiencing engine failure in the shipping lane, well, they can't steer or move their ship. They're going to need to communicate with other ships and let them know that there's a problem. So one thing they might communicate, they might hoist up flags F, D, K, and V, and you can see the flags on that slide there: Foxtrot, Delta, Kilo, and Victor. Each one of those flags has a message to send along. They would be saying Foxtrot, which is that first flag that, hey, we're disabled. Delta flag means keep clear. Then they also like to communicate Kilo flag, which is they would like to communicate, hey, we need to talk to any ships that are nearby, and then also that they require assistance, and that's that Victor flag. Each one of those flags, with the exception of Romeo, the R flag for some reason, has a safety message tied to it, which makes clear communication quick and efficient amongst everyone navigating the high seas. All right, so that's a little bit of introduction to the International Code of Signals. What we're going to do now, I'm going to do a quick little activity, just so you can kind of see, looking up the flags to determine the letter. We'll do a quick word scramble. And then Abby will go through what you would do if you want to create a really attractive class banner using these International Code of Signal flags for your classroom. So if we look at this example right here, here's all of our letters and numbers again. We're going to quickly descramble this 5-letter word. So I'll kind of give you just a few seconds between each slide, but let's start with that flag in the top left, the red and white flag. If you look to try to match that red and white flag up on the chart, you see that it's H, or hotel is the, all right. Now the next flag is the one right next to the H, and you look and you find, what's that? Oh, okay. All right, that next letter is R, or Romeo. And then going underneath to the blue square in the middle, we figure out that is S, or Sierra. And then you look at the next letter, which is K, or Kilo. And finally, that last one of the only two that we talked about that are not square, is Alpha. You might also recognize Alpha if you're on the water and your family does any diving as the international dive flag for diver down. That's the message of the Alpha flag. So I'll give you a second to unscramble that word of a sea creature that we're all very familiar with in our coastal waters, the shark. All right. So obviously there's a greater message behind these flags. This was just kind of just a little quick activity to introduce you to some of them. All right, now I will turn it over to Abby to talk about creating a banner with these flags for your classroom.
Thanks, Grant. That was great word scramble. So hi, it's Abby again. What we're going to do is build a class banner. As Chris mentioned before, there are some supplies that you all need, and you can also do this at home. You need paper, red crayon, blue crayon, black crayon, and a yellow crayon, some string, and a hole punch. So very simple materials needed. So what you're going to do is select a saying for the class banner. So it should be the same numbers or letters as students. So if you have 20 students and you go to Mount Vernon Elementary School, you can write Mount Vernon Unicorns 2020. And so each student gets a letter or a number. And then you're going to color the letter on the piece of paper or the cardstock. And you want to make it big, because if you're out on a boat and it's something really, really small, the other boats aren't going to be able to see it. So color the whole piece of paper. And then you're going to string it together and hang it in the classroom. And if you're doing this at home, you can do something a little bit more simple to hang in your room, like Go Science, I love science, I love the water, something fun, or even your first and last name. And it's going to be a fun little perk that Chris has put together is the first 3 classrooms to send us a photo of their banner hung up in their class. We will mail them something. So once you guys figure out your class banner, you guys color it, and then you hang it up, send us a photo, and we'll put our email addresses on the next slide for you all to get a little surprise for the first 3 classes. And this is an example that we did in person 2 years ago. And you can see the students coloring the flags, and then we have it hung up here. And I will go ahead and put up our email addresses so you guys can take a screenshot of that. So when you get your banners done, you can send us a photo of it. And then while we're going to go into the questions, I'm going to go ahead and pull up this photo of the International Code of Signals to help you build your class banner, and pass it back to Chris.
Thanks, Abby. While you're looking at the flags and thinking about the banners that you might want to create, we're going to ask Kara, our moderator, if we have any questions coming in.
Thank you, Chris and Abby and Grant. That was so cool. I do have some questions for you all that are coming in, and maybe we're going to get some more, although I guess we're having some technical difficulties. But.
We're standing between our students and lunch, so we totally understand.
Oh, yeah. I think this is a question from Academy at the Lakes, and I think they might be asking about the HAB scope. They want to know how long it takes to make something like that.
So the process for the development took several years, both because of funding and for developing the technology. Once the technology was done, now we also have to keep up with technologies as they change, right? So the iPods were the original source for the processing, but now those are being discontinued. And so the team is looking at using something called Raspberry Pi. And so it's constantly evolving to keep up with the changes. So the actual process was roughly 2 years ago, and it went operational about 3 months ago. So transitioning from that research phase to a real forecast that people can use on a daily basis takes quite a bit of time.
How about another one here from Academy at the Lakes? Has a scientist ever been injured researching the ocean?
Well, yes, that just goes without saying. There's different ways of being injured. I mean, you can think about somebody who's gotten really seasick, being out at sea for months and being dehydrated and have to be evacuated. That's sick, right? But it's not typically what you think about. I've been at sea. I've been in the Antarctic when people have been injured by a leopard seal. mostly the precautions and the safety measures that are in place are very rigorous, and there's very low injury rate. It's usually accidental if somebody slipped, more like a back injury because somebody lifted something heavy the wrong way, or the pitch and roll of the ship may have moved and shifted your center of gravity. But injuries on the vessels themselves, there's very high safety protocols that are followed and adhered to. So it's very rare to hear about that.
How about another question from Academy at the Lakes? They'd like to know what you do when the research equipment breaks, which that does happen.
You expect that it will. It's why we have what's called redundant systems. You very rarely, unless it's an extremely expensive piece of equipment that might be a prototype and there aren't more of them, you always go out with backup and redundant. We have a saying, don't throw it over the side if you can't afford to lose it, because electronics and salt don't typically mix. And so leaks can happen, cables can break, a lot of things can happen, but typically you're redundant. You plan and you double plan and you triple plan and you're careful.
I imagine that's especially true when you're going as far as Antarctica.
Especially true, yes. And recently, even just going out here in the Gulf of Mexico, ship time's very expensive. So you have to be super organized. It's one of the skills, if you are thinking about this as a career, being very organized. Project managers are critical parts of the project. Even if they don't go out, that organizational piece is critical.
Another question from Academy at the Lakes. They want to know how big the buoy is. You've got a kind of a good demonstration.
This particular one here is only about 3 feet across. A real buoy is often is a 3-meter disc buoy. Can be, it's usually in that range, but they can be bigger, 10 feet. They can be 12, 13 feet. It just depends how much of a payload in the weight of the equipment is going to be on it that the flotation must support. So that's really what determines how big the buoy is going to be and how big the A-frame on the ship is, right? Because you have to be able to deploy it and retrieve it when you need to. So those are kind of conditions that go into guiding the development of the size.
Wonderful. I don't see any more questions at the moment. Keep them coming in. I had a question. I was wondering about the flags that you see that are like a weather flag, like a hurricane flag. Are those also part of this ship communication?
No, those have some of their own signals. I'm going to hand off to Grant because he's handling our International Code of Signals. But
Yep. Yeah, so those hurricane flags that determine, or you flag warning flags on the beach. It's using flags as a visual way to communicate that is a very common strategy. But that they're not tied into the International Code of Signals. Great question.
It's US, yeah.
Very good. I hope everybody is working on their International Code of Signals banner for their classroom, and I'm going to send that back to you all. Very cool. Do we have any more questions out there, Carmen? She's saying no, that we don't. I think we answered all of our questions that were here. Oh, there's one more question that was not completely answered. They Academy at the Lakes wanted to know, how long do you research a topic? Anybody want to answer that one?
Yeah, so it really depends on the topic. Like within Socorro, we've had buoys out in the Gulf of Mexico for decades, so about 2 decades, for 20 years. And what they're doing is they're telling us how the ocean is changing, because you can't know if the water is getting warmer just off of 1 year of data set. You need multiple years. So it really just depends. And then as Chris mentioned, gliders can go in the water for 30 days and they research events. So if there's a harmful algal bloom, that could last 5 days, it could last 30 days. So we send out a glider to tell us what's going on beneath the water column. And as it seesaws up and down, it collects data, sends it back to us, and we're able to quantify what's happening in the ocean and figure out what that event, the harmful algal bloom event, is, how it's progressing. I hope that answers the question.
I think so. I think that was great. And of course, we're all very interested in harmful algal blooms this year. So hopefully everybody learned a little bit about how you all observe them. I think that's all the time that we have at the moment. So I want to thank you all from the Gulf of Mexico Coastal Ocean Observing System and Sikora. Thank you for joining us. And we'll be back shortly with our next presenter.
Thanks for hosting us, and
Thank you.
David and your fabulous St. Pete team. This has been great. Thanks.
Thanks all. Have a good day.